All right. Welcome back, everyone. For today's pre seminar, we have our very own Giovanni, who will be talking about Hopf algebras in braided monoidal categories. Take it away.
Thank you. So to introduce Antonio's talk later, which will be about differential calculi on over braided Hopf algebras, we will take a look at what these objects are. And let me start by recalling the definition of a braided monoidal category. So braiding for monoidal category and the monoidal category, let me call it M, tensor product, monoidal unit, and then you have three natural isomorphism, the associator and the unitors. But you know that you can morally forget about these three because every monoidal category is equivalent by MacLane's coherence theorem to a strict one, so one in which these natural isomorphisms are the identities. So a braiding for a monoidal category is a natural isomorphism sigma from this functor here to this other functor of components for all objects x and y in the category. Sigma xy is an isomorphism from the object x tensor y to y tensor x. And just to fix the notation, on an element x tensor y, the braiding is denoted by these Greek indexes that is a short notation for a sum in the opposite tensor product. From this functor to this functor. Sorry, the associator. This is the associator. It's from tensor to opposite tensor. Yeah, I went in automatic pilot. Okay. And yeah, and this braiding, so this natural isomorphism has to, well, its components have to satisfy the hexagon relations, which for a general braiding where you have some non-trivial associator tell you the relationship between the braiding and the associator. But let me write them in a compact way, like this. So for some elements, x, y, and z in objects in the category, the hexagon relations, if we take the associators to be the identity, look like this. So you have one with our notation, so with the Greek indexes, that tells you that if you braid x tensor y with z, this is the same of braiding first y and z and then x and z. So you will have some Greek indexes like this. And the other one is similar. So you braid y tensor z with x now. And this will be the same as braiding first x and y and then x and z. Like this. And then a braided monoidal category is a monoidal category that admits such a natural isomorphism. So braided the monoidal category together with a braiding sigma. Okay. Then to give you some examples of braided monoidal categories, let me recall what is a quasi-triangular Hopf algebra, since many... Yeah, sure.
Very basic.
Yeah.
Can you explain this alphabetic now?
Yeah. So these are these relations. You want the hexagon relations. So this is the image of the component of the braiding labeled by objects x and y on some element x tensor y. And these will be the hexagon relations where you take the associators to be the identities. Because, for example, this is what? This is, well, let me take this so that I don't make mistakes. This sigma of x tensor y z on x tensor y tensor z. This has to be equal to this other guy here, which is sigma on x z tensor identity after identity tensor sigma on y z, I guess.
You show the actual hexagon.
Yeah, the hexagon is an hexagon when you have also the associators. Yeah, well, the identity, I can draw it with the identities. So the hexagon is, so you start from x tensor y tensor z. Here you braid with sigma of x tensor y z. Then you rebracket with the associator. And here you rebracket with the associator. Yes, sorry, x, y, and z. Then you braid these two. Well, you do identity tensor braiding. So x tensor z tensor y. Then again you rebracket. Yeah. And from here, identity. Wait, you messed this up. Yeah, probably. So yeah, I know, you know what I mean. This is this. Okay, I mean, to draw everything is too much time.
The foundation can be explained with the example.
Yeah, also you can yeah. I mean, the alpha notation is just telling you this will be some morphism in the category, and in general you will land in the opposite tensor product. This is a finite sum in there usually. So I will give you an example now. And okay, so for example, I will do everything in one go now. So recall that H, a quasi-triangular B-algebra, is a B-algebra plus an invertible element where there exists an invertible element R, called the R matrix, that is usually denoted by these indexes, that lives in the tensor product of the B-algebra with itself, satisfying the following almost co-commutativity condition. So if I twist the coproduct of H by the R matrix, I get the opposite coproduct. And then there are some relations. Again, satisfied by the R matrix with respect to the coproduct. If you have such an object, then you can produce examples of braided monoidal categories. In particular, if let H be a B-algebra. Then the category of left modules over H with the vector space tensor product and the ground field as a monoidal unit is monoidal. Where for every two modules M and N, then the tensor product is again a module by this action here. So any element H on any element of the tensor product is defined to be H1 on N, tensor H2 on N. So the B-algebra structure of H gives us a monoidal structure on the category of is a quasi-triangular B-algebra. This is equivalent to saying that the category of modules is also braided. So with braiding given by this sigma R in terms of the R matrix. So the braiding on some objects will be given by the action of the flip of the R matrix on the flip. Sorry. Like this. So these two statements are equivalent. So the category of modules over a quasi-triangular B-algebra is braided. And you can do the same for co-quasi-triangular B-algebras. The category of comodules is monoidal if you have a B-algebra. And if this B-algebra is co-quasi-triangular, the category of comodules is braided. And okay, then another example of braided monoidal category is that of the category of Dieter-Drinfeld modules. So let H be a Hopf algebra now. Then the category of Dieter-Drinfeld modules, which is denoted by this, is the category that has as objects these objects V that are both left H modules and left H comodules. And so what do I mean? That for every object V in that category, I have an action of H onto V.
Excuse me, do you hear me?
Yes.
Sorry for interrupting, but can you move the camera? Not you, but yeah, thanks. Great.
Thank you. And I have a coaction, which by Zwiddler notation, also here, I didn't say this, but this is the Zwiddler notation for the coproduct. Is H1, tensor H2 will be the coproduct of H. And here the coaction on V is denoted by V minus 1 tensor V0. And objects are both left modules and left H comodules, such that if I first act and then I coact, I get this compatibility. And this category arises all over the place, even though this seems a rather strange formula. But these are objects, then morphisms are left H linear maps and left H collinear maps. And the monoidal structure here is again, so if I take V and W in Dieter-Drinfeld, then V tensor W here, sorry, tensor W is injected Drinfeld by the diagonal action that I already written. So it's an H module by that action, and it's an H comodule by the diagonal coaction, which is like this on elements V tensor W of the object V tensor W. So I coact on both, and then I multiply the legs that live in the Hopf algebra. And you can check that this diagonal coaction and that diagonal action satisfy this compatibility again. And then it is also braided. So this category where I take the vector space tensor product and the ground field has a braiding sigma that on objects VW is defined to be I coact on V and then I act on W. This is the Jeter-Drinfeld braiding. It is a morphism in the category. It is an isomorphism when the antipode is invertible. And this makes it, so I should say H as an invertible antipode. Okay, so then I wanted to tell you about braided Hopf algebras. So Hopf algebras in such categories. And to understand this, let's first think about what does it mean to have an algebra object in a braided monoidal category. So A mu eta, where eta is the unit map, so it's the unit of the algebra, is an associative unital algebra in a braided monoidal category. Okay, so what I wanted to tell you is not what this means. This essentially just means that A is an object in the category and these are morphisms in the category. But then how is A tensor A again an associative unital algebra? Is an associative unital algebra by this multiplication. So I'll show it on elements A, B, C, and D in A. So if I multiply an object A tensor B, sorry, an element A tensor B with an element C tensor D, this is defined to be A alpha C tensor alpha B D, where again here we use our notation. So essentially to keep the order, to make this product associative, you have to flip these two, and you have to flip them using a morphism in the category, and this is, you can do it if you have a braiding in the category. For vector spaces, this is just a flip. In general, this is how the tensor product of an algebra with itself, or you can take even tensor products of different algebras. This is how it is an associative algebra again. And so now we can define a braided Hopf algebra. So, okay, maybe a braided B algebra is a 5-tuple. Let me call it B underlined, where I have B, a vector space, and then I have a unit, a multiplication, a co-unit, and a co-multiplication, all underlined because they are morphisms in a braided monoidal category. So a braided B algebra in a braided monoidal category and tensor A sigma is a 6-tuple such that B mu eta is an associative algebra in the category. B epsilon delta is a co-associative coalgebra in the category, and which means these are morphisms in the category. But then you have to ask for the bialgebra structure that delta here is a morphism of algebras in the category. And we just saw here how the tensor product of the algebra with itself is an algebra in the category. So the compatibility between the coalgebra structure and the algebra structure looks like this. So now delta of a product will be A of a product of elements A and B will be A1 alpha B1 tensor alpha A2 B2, where by this upper index is, I mean, it's a notation for the coproduct in a braided category. We use Svidler indexes, but upstairs. So, and this is for all A and B in B. Plus, if you have an antipode, if there exists a map S underlined from B to B called the antipode, such that the usual compatibilities are satisfied, and also flipping these two, then B underlined is a Hopf algebra in a braided monoidal category or a braided Hopf algebra. And this is a braided Hopf algebra, or is called a braided Hopf algebra in M underlined in the braided category. So an example of this, even though I cannot write everything down, is just to mention it. You can take what is called the quantum plane. That is a very simple algebra generated by elements x and y, modulo the relations xy equals, well, xy minus qyx. This is an algebra, and this is a braided Hopf algebra by this coproduct. Let me call it a generator Z. Z is in the set xy. So this is a braided Hopf algebra in a category that I will tell you now by this primitive coproduct and by this antipode where I take minus the generator. You extend these as morphisms of algebras and anti-algebras, and this is a braided Hopf algebra in the category of Jeter-Drinfeld modules over OQGL2. Meaning that there exists an action of OQGL2 on this and a coaction that are Jeter-Drinfeld compatible. And with this structure, the quantum plane, that is the name of this, becomes a braided Hopf algebra in there. Now, other examples of braided Hopf algebras come from a process that is called transmutation. This is due to Majid. So you have a proposition that tells you that if H delta mu eta delta epsilon S is a Hopf algebra, that is quasi-triangular. So let me add also the R matrix here. Then H as a vector space with the same multiplication, the same unit, the same co-unit, and a transmuted coproduct and antipode is a braided Hopf algebra in in the category of modules, of left modules over H that, as we saw earlier, is braided because H is quasi-triangular. And how do these modified coproduct and antipode look? So on elements H in H underlined, these look like this. So you take the coproduct and then you have the R matrix coming in. So this is Ri, tensor Ri, and you have the second leg first, and then the first leg acts on the second leg of the coproduct on H, the original coproduct on H. And this antipode, this modified antipode looks like this. So with this structure, this is a braided Hopf algebra in here. And how is this module in here? You just take the adjoint, the left adjoint action of H on itself. And so you can produce a lot of examples of braided Hopf algebra if you start with a quasi-triangular, and the same with a quasi-triangular Hopf algebra, and the same can be done for co-quasi-triangular Hopf algebras. You obtain by transmutation an Hopf algebra with a modified product and antipode in the category of comodules of the co-quasi-triangular Hopf algebra that is braided again by a similar argument as before. For example, you can take this very simple algebra that is the Zwiedler Hopf algebra. That is the algebra generated by elements 1, G, and X. This is the dimension of the algebra. You can also, because the relations are G squared equals 1, X squared equals 0, and Gx equals minus Xg. So this algebra here is a co-quasi-triangular Hopf algebra by the coproduct X tensor 1 plus G tensor X on X, and on G we have a group-like structure. With this coproduct and with an antipode that, I mean, it's not important, just to cut it short, you can transmute this Hopf algebra because it has an R matrix. So R over H4 is 1/2 1 tensor 1 plus 1 tensor G plus G tensor 1 minus G tensor G. So you can take this information that gives you a quasi-triangular Hopf algebra and transmute it with these formulas. And what you get is a more symmetric Hopf algebra in the category of modules over the Zwiedler Hopf algebra. The antipode takes a minus and the G remains group-like. So a question would be, what if I take this more symmetric structure and I put a calculus on top of this? Can also a differential calculus have more symmetry and then once you can find on the original Hopf algebra? And I have 1 minute maybe. So I would like to finish with bosonizations, which are construction, again, due to Majid and Radford. And they do the opposite of transmutation, if you like, because transmutation makes you start with a Hopf algebra and produces one in a non-trivial braided category. Here, if you start with a braided Hopf algebra, you get a Hopf algebra in vector spaces. So let H be a Hopf algebra and B a braided, be underlined, a braided Hopf algebra in the category of Vietter-Drinfeld modules over H, then this Hopf algebra that is called the smash product Hopf algebra. Well, for now it's not an Hopf algebra, but the proposition tells you that it is. So this as a vector space is B tensor H, and this is just a different notation for the tensor product because it helps you keeping track of where are you taking coproducts and whatnot. So this is as a vector space B tensor H, and it has a multiplication, a unit, a co-multiplication, and a co-unit that I will define in a bit, as well as an antipode. On all elements B smash H in B smash H, these maps look like this. So the multiplication, well, and let me say also an element C smash K in B tensor, in B smash H. So the multiplication of such two elements in the smash product of algebra will look like this. So you have B, H1 on C, H2K. Then you have that the coproduct on any element looks like this. So B1, this is the first leg of the coproduct on B that is braided, so we use an upper index. Smash B2 minus 1 H1. So on the second leg, I coact since B is in Vietter-Drinfeld, and so there is a coaction. And then I have the rest, B2 0, smash H2. And then I have also an antipode, which is not very much important, but then you can prove that with all the structure of B, that is a braided Hopf algebra in a Vietter-Drinfeld category, and the structure of H, with these maps, the tensor product B tensor H becomes an Hopf algebra. So this is an Hopf algebra in vector spaces. And for example, you could take CQ2, that is in Vietter-Drinfeld of OQGL2, take the tensor product, CQ2 tensor OQGL2, that will be an Hopf algebra in vector spaces that you can think of as the quantum analog of the semidirect product of the affine extension of GL2 semidirect product with R2. And also the coproduct here, you can think of it as coming out from the matrix multiplication of elements in GL2 semidirect product R2. This formula here comes from there if you want. Yeah, that's it. This is what I wanted to tell you.
Thank you, Giovanni. Any questions from the audience?
Yeah, maybe I have a question.
No.
I don't know, Tom.
Ray was just about to ask a question. You two can fight over.
Okay, Ray wins, but only if he uses the microphone, so we can also hear him.
I think you should be able to hear.
Okay.
Yeah.
This maybe just focusing on the example.
Yes.
Wait, I should have thought about this before I did the calculation. Thomas, go first, please.
Yeah.
So maybe we had the same question because I was also, so my question was also about the example. So if we take the quantum plane, seen as a braided algebra in the Riemann of GLQ2, and you build this smack product algebra, what do you get? So is it somehow clear what Hopf algebra you will get there?
If you take the smash product, if you take the bosonization of what? I didn't hear the start.
Of the quantum plane
Yeah.
and GLQ2.
You get an Hopf algebra CQ2 smash GLQ2. And yeah, this is the operations that you get. Is it clearer in the sense that does it have an interpretation? Yeah, because
exactly.
you can think of GL2. I don't remember the direction of the semi-direct product symbol, but then elements in here I think look something like 1, and then no, sorry. Here you have translations. And if you multiply two elements of this form, x prime, y prime, a prime, b prime, c prime, d prime. So, and you construct the coproduct on generators by this matrix multiplication in the usual way you can remember from matrix quantum groups, let's say, then you get this. You get these for CQ2. Like you can check that the formulas you get from the bosonization construction are the ones you get from here. So in this sense, it is the quantum version of the semi-direct product.
Nice, thank you.
So for the Sweetler-Hopf algebra,
Yeah.
what's the dimension? Is that clear?
It's 4.
4, that's where the 4 comes from, right?
Yes, because these relations, I mean, the vectors are just x, g, g, x, and the unit.
Yeah. So then if I have a Hopf algebra, well, I have at least an algebra map that goes from H4 to the group algebra of G2. I'm just going to look at the subalgebra generator. I'm going to project down by sending G to G, X to 0, and 1 to 1. And then you get it like an analog, something that looks like the invariance would be something that looks like a flag.
Yeah, because the coproduct on X looks like...
Yeah, exactly. And then you're going to get, if you take then the tangent space to be the thing generated by, no, actually just to be X. Yes. That should work, and then you get a calculus on this thing.
Yes, it should work.
And then I wonder if this gives us a Ian Baxter. Okay, yeah, just a comment. And this thing is self-dual, I guess.
Yes. Yeah. You can also look at it as a co-quasi-triangular Hopf algebra, obviously, and transmute it into a braided Hopf algebra in the category of right modules.
Can you see what the co-quasi-triangular structure is?
We did it, but I don't remember. Yeah. You cannot. Yeah, we wanted to do that, but the R matrix, as far as I understand, does not live exactly in the tensor product of UQG with itself. So then this construction, I mean, this is an infinite sum. This is an infinite sum.
But then.
On the side of OQG, you could transmute OQ as to 2, yeah.
Yeah. I mean, so
but it's a lot of calculation.
Are genuinely co-quasi-triangular, so you can take the transmutation process, and
then there may be a 3D calculus that is bicovariant on there.
I feel that Majid did something like this. Maybe we had that discussion.
That is the idea of.
So if you were to take the transmutation of OQSU2,
Yeah.
then it's okay. The
It's
core
not-
version of
it's-
transmutation is not there. Well, this is the bosonides, but
Tell you if you want.
yeah, I mean, basically, as an algebra, it's what gets this one.
As when you transmute a quasi-triangular Hopf algebra into a braided Hopf algebra in the category of modules, you change the co-product.
Okay, so
But
as an
the other side, you change the multiplication.
Aha.
So the bimodule structure on a calculus on top will all be different, maybe also. That's the idea.
Okay, thank you.
There was one raised hand from Freddie, so feel free to speak.
Yeah, hello. So I have two questions. So the first question is in the definition of the braided Hopf algebra, braided bialgebra.
Yeah.
So what does the as you have the definition of a associative algebra and coalgebra in the braided category? What does that mean? There is a compatibility.
A little bit fast, yes. I mean, it means that, well, it needs to be an associative algebra, but it is an monoidal category, so you should be able to take tensor product of algebras and still have an algebra. So this is what I meant here. But yeah, these statements by themselves just mean that I have an associative algebra where the multiplication and unit are morphisms in the category. And then to have a bialgebra structure, you need a notion of algebra on the tensor product of the algebra with itself, because the coproduct has to be a morphism of algebras from the algebra A to the algebra A tensor A.
Yeah.
So that's what I meant. Or equivalently, the multiplication has to be a coalgebra morphism. Also, you can take tensor product of coalgebras in monoidal categories that are braided, because you need to flip things in order to maintain orders and keep the algebra associative or the coalgebra co-associative.
Okay, yeah. So and the other question is in this process of the transmutation and bosonization. So in the transmutation, you start with a triangular Hopf algebra.
Yes.
So and you apply the transmutation, and after the transmutation, you apply the bosonization. You recover the algebra in some sense.
Yeah, I guess the category of modules over the quasi-triangular Hopf algebras is equivalent to the category of Dieter-Drinfeld modules. So you can take the functor to the category of Dieter-Drinfeld module after transmuting, and then you will have a braided Hopf algebra, I guess, in Dieter-Drinfeld, and then you can take a bosonization. And I don't know what you get. Maybe you get, I don't know. I don't know. The Drinfeld, I will say stuff that's not correct, but yeah, would say that. Okay.
I will stop you before you say anything
Yeah, yeah.
incorrect. Let us thank Giovanni again. And then we will just take a 5-minute break and be back in 5 minutes from now for the main seminar.
Ben.
Yeah.
This,
Yes.
I'll give it to Antonio.
Yeah, it's good. You got magnets.